All right. So, Abhinav, I think also you can start the recordings.
Yeah.
All right. So, hi everyone. Very good evening to all of you. It's always great to catch up on every Wednesday and Saturday. In spite of your schedules and weekend plans, so a lot of people still attend these sessions. On every every Saturday and Wednesdays from Decibels that we've been hosting. I'm glad to see your participation. And topics such as this are very specific, and we only see a very specific audience to take part in this kind of a sessions. So thanks again for everyone who is here for participating in this session. And as per today's topic, which is on introduction to cell balancing, and this topic will be delivered by one of our team of experts. That will be Abhinav, and he's a battery algorithm engineer at Decibels Lab. So you would know the highlight of this topic as such as cell balancing. It is a very, very, very important activity that take care not just about balancing cells, but it gives you a lot of importance in terms of algorithms. The reason why being is, let's say, if you want to use the best out of the battery pack, it is always ensured that if the cells are balanced, you will be able to extract the most of the energy to the last sip of the juice in the cells, right? Because if you're among the 13 series cells, if you have, let's say, one or two cells are at lower SOC or a lower voltage, then you definitely have problems because that cell will go to an under voltage if you still continue to discharge, right? And in similar to this, as I said, so we will also have a problems of a cell safety if we do not have properly balanced cells as well. In case you might have seen a lot of incidents that are happening in recent days about the fires being caught up for the battery packs, right? You have seen some of the incidents. The companies have accepted that because the battery pack had imbalanced cells, right? Let's say one cell is at when you're charging the vehicle or battery pack, let's say one cell is at 4.2 and other cells are at, let's say, 3.8, and you start to overcharge a cell. The battery management system should be able to take care of it, but in cases it doesn't, and then your charger still try to pump the energy into the battery pack, it could cause a serious hazardous when you do a overcharging. But also in circumstances such as under voltage issues, so if it is a imbalanced battery pack, so then you try to discharge the cell little below its specific values, it could also impact the cell's life, and that impact is irreversible in many cases. Right, so it's just not about taking out energy from the cell and it just drains out at a resistor, or if it is an active balancing, it's just not to take out the energy, store it somewhere, put it back to the cell. The definite scope and importance of such activity of cell balancing is really, really predominant, and it is desirably required at today's industrial battery management system, and specifically for automotive applications as well. So with this keen interest, Decibels has been working on various different projects to develop algorithms for a battery management system. In that regards of it, we have a master course where we are teaching you everything about algorithms for cell balancing as well. But as of today's topic is concerned, so we will be giving you a very brief introduction to an overview of cell balancing and technologies, and how does it really happens inside the whole battery management system altogether. So with that base note, I will hand over the session to Abhinav, and over to you guys as well. Thank you, Abhinav, for giving a few minutes for me to give you a brief introduction, and just give you a heads up with Abhinav's profile. So Abhinav is a graduate in mechanical engineering. He studied in Hans University at Netherlands. And he's been with Decibels for quite some time, working on batteries, testing cells, characterizing cells, collecting a lot of data, and developing algorithms using embedded toolboxes, and creating algorithms in continuation to that. It gives a great pleasure to have you on the session here today, Abhinav, and over to you. Thank you.
Yeah, thank you, sir. Thank you very much for the introduction. So, a warm welcome to all to this session on Introduction to Self-Balancing. So, my name is Abhinav Arvind, and currently I'm working as a battery algorithm development engineer at Decibels Lab. So, I work with MATLAB and Simulink, where I develop battery and cell models, and I also test them in different scenarios. I'm also currently involved in live cell testing, where we use cell testing machines to characterize cell behaviors. And I'm also currently working on battery management system development. Yeah. So today in this webinar, we will have a look at cell balancing and why cell balancing is needed, why it is so important in today's battery pack systems, and what are the different approaches to to complete cell balancing in any battery pack. Okay. So yeah, today is the this is the content for today's session. So we'll start with introduction of battery and cell balancing. So what exactly are imbalanced cells? What does that mean? What are the causes for imbalancing? And what is the effects, the side effects or the dangerous side effects of imbalanced cells? And then we come to the need for cell balancing. And then finally, we come to the definition. So with this, we will then progress with the different classification. So what that means is we'll be looking at few of the different methods in which balancing can be achieved, right? So we'll be looking at passive, active, and lossless balancing. Okay, so we will have a brief look at all of these classified methods, right? So what are unbalanced cells? Well, unbalanced cells are basically cells that suppose in a battery pack there are so many number of cells, right? So there are cells that can have very high voltage. Yeah, there are cells that can have very low voltage, and then there will be cells that are exactly within the correct operating limit as well. Yeah, so in a battery pack there can be all these different types of cells, and they can affect the battery pack performance in various different ways. Yeah, so in this way, I mean, even during charging or during discharging, this can affect the performance of the battery pack. Yeah, so for example, let's say that a battery pack is currently discharging. Okay, so that means it is supplying power. So at certain times there could be few cells that have very low voltage. Yeah, especially in this example, it is cell number 7. So what this can mean is that once this voltage of this cell has reached such low voltage values, it will start undergoing a phenomenon called deep discharge. Okay, it will undergo a phenomenon called deep discharge. So what that means is that it is being discharged beyond its safety limit, and that can cause irreversible damage to the cell during operation, and it can also start to age the cell or damage the cell internally. Yeah, so this is why it is important that all of these cells stay within the operating limit, and this not only applies to discharge but also applies to charging. So you can see here an overcharged cell. So similar to in a discharge situation, if a cell reaches dangerously high voltage levels, it can start entering something called as over voltage. So similar to deep discharge, we also have something called as over voltage. Yeah, so over voltage is basically crossing the upper safety limit or upper safety voltage limit, yeah, in terms of charging. So this can cause many situations, many dangerous situations like gassing. Okay, gassing is where excessive chemical reactions start to occur and release some pretty toxic gases from the cell. It can start to heat up the cell, and then eventually the cell can undergo thermal runaway. Right? So thermal runaway is a phenomenon where the cell begins to heat up so much that it catches fire, and it spreads this heat and fire to all the surrounding cells. Yeah, so this can cause cells to be cells to catch fire, and finally the entire battery pack will catch fire. Yeah, so these situations, like even in very recent situations, we've seen where Ola S1, specifically the Ola S1 model, suddenly catches fire. Yeah, That's because of an improperly balanced battery pack, which the battery management system fails to recognize. Yeah. So all these are, some of the effects that we face. These are some of the effects that will be faced if the cells are unbalanced, left unbalanced in an entire battery pack. Yeah. So there could be different causes of cell imbalance, right? So there are certain voltage readings that can go wrong. There can be certain voltage parameterization that could go wrong. So different open circuit voltages for each cell that could lead to different states of charges. And because of this, if cells are being discharged at or charged at different rates, then one cell can reach the upper limit faster than other cells, causing it to be imbalanced. Yeah. So this is a consequence of different open circuit voltages that can happen due to operating it at different temperatures or operating it at different internal resistance. So cells, all electrochemical cells, whether it's lithium or lead acid or any electrochemical cell, has a certain bit of internal resistance. Yeah, and over time, this internal resistance can cause some small minor changes in the output of the cell. That is the voltage of the cell, and because of this it can over time the cells will start to achieve different voltage levels. Yeah, and thereby that can cause imbalance or incorrect readings in voltage. Yeah, one more thing, one of the more important ones is the long-term effects called the aging effect, right? So over repeated usage, cells start to age, which means that the internal components of the cell start to get damaged, and it won't be effectively be able to give out the same voltage level as it was when it was brand new. So like for example, a lithium ion cell has a maximum voltage of 4.2 volts at its peak when it's brand new. So this is for the new cell, and for an old cell or for an aged cell it would be something like much reduced value like 3.7 or 3.6 value, 3.6 volts. Yeah, so this would be your maximum voltage, right? And this can cause some amount of imbalance in the battery packs. Yeah, another cause would be because of changes in temperature, right? Changes in operating temperature or changes even within the cell temperature itself, which can cause changes in the chemical reactions occurring inside the cell, and that would then directly affect the voltage of the cell. Yeah, so all of these are like physical phenomenon which can cause imbalances within the cell. Okay, and coming to like uncontrolled factors, so something which is not nothing much can be done about it, and that would come under manufacturing defects and assembly defects. Okay, so like during manufacturing there'll be like different cells from different brands being manufactured, and the manufacturing processes that are implemented in order to assemble and manufacture the cell, they could vary a little bit, and that can cause some small amount of defects or small amount of changes in the internal portions of the cell. Yeah, and also coming to assembly defects, so different methods of assembly, different methods of arrangement, and different methods of fixing the cells, that can cause some microscopic defects like on the cathode or on the anode or within the electrolyte, right? So all of this can lead to a small change in voltage. It won't affect the battery pack or the cell immediately, right? But these will have a long-term effect. Yeah, so it's not immediate, it won't happen instantaneously, but there will be some long-term effect that will be observed. So over time you will see that one cell will start showing slightly different voltage readings than another cell. Yeah, so all these could be potential causes of imbalanced cells inside a battery pack. Yeah, so what are the effects of an imbalanced cell or effect of imbalanced cells, right? So the first and foremost thing is the overall operational life of the battery pack reduces. Okay, so what that means, so we took a look where we saw that one cell, if it discharges faster than other cells, then what that means is the battery pack will only have a life which is equal to the cell that is discharging much faster. Yeah, so let's say that we consider the previous example itself. Suppose we have n number of cells, right? So there are like n number of cells, and let's say this is let's say we'll just consider three cells. So let's say first cell discharges normally, second cell also discharges normally, but then the third cell discharges very rapidly, right? So it discharges much faster than cell number 1 and cell number 2. So the entire battery pack that is made up of these cells will only last as much as cell number 3. So it is going to have an operational life of as whatever it is that you see from 3. So that is one of the major drawbacks. Yeah. The other one is that the overall state of charge of the entire battery pack will never achieve true 100% due to some of the cells which will be limited or will be having limited voltage, right? So again, as we saw, some of the cells in the diagram, we saw that some cells will reach 4.2 volts pretty quickly, but some cells will not reach it, no matter how much time you give it. And that can happen again because of aging. That can limit the charging limit to some cells. Yeah, and because of that, the entire battery pack will never achieve a true state of charge of 100%. Okay, so that means reduced voltage window. Okay, so that means reduced voltage window. So then on another thing is that if imbalance is like continued, then cells that are having very low voltage can enter into deep discharge zone. So we had taken a look at the previous slide where we saw an example of a cell with very low voltage. So once it enters this deep discharge zone, continuously, if it is going to be exposed to this deep discharge zone, recovery is not possible. So what that means is that it is going to be permanently damaged, and no matter how many times you try to charge it up, it will not be able to recover the complete voltage, and it will give you incomplete life, right? So that means that the cell has been permanently defected. Yeah. So same to overcharged cells can enter into over voltage zone and cause thermal runaway, gassing, heating, and can even explode the cell. Yeah. So again, the voltage window of the pack will be like reduced very much. So like uh, so if you consider the voltage graph, so for a lithium ion cell, this is the voltage graph, right? And your voltage window is calculated like somewhere between 85%, yeah, to around 20%. Yes. But if you look at all the voltage graphs of all the cells put together, let's say if some of the cells are only partially charged, say till about here, say about till 60%, right? So then the entire battery pack will only have an effective battery pack percentage or a voltage window of 60% of its actual capacity. Yeah. So that is something that is something one of the other drawbacks of the imbalanced battery pack, which will then directly affect the range of the vehicle. Yeah. So nowadays, like the most important thing is range, right? So if this happens, then the range of the vehicle will be directly affected. It will be reduced. Yeah. So these are some of the major drawbacks. Another drawback is thermal runaway, so which we had discussed this previously. So all these drawbacks give the need for balancing. Okay, this gives the rise to need for balancing. Okay, so then summarizing it briefly, cell balancing is done to prevent the cells from escaping their nominal operation region, right? So if this is a cell, there'll be a nominal upper voltage and there'll be a lower voltage. Yeah. So keeping the cells within these limits, both in terms of charging and discharging, is very crucial, right? Because if you continuously start to operate outside these zones, it will start to rapidly degrade this cell. Yeah. So again, which is a direct consequence to the first point, it is to prevent overcharge and over discharge of the cells. So improve the overall usage window of the cell, right? And to ensure that the battery pack can achieve at least up to 100% SOC whenever it is needed. Yeah. So especially when long distance of travel is preferred, right? So let's say you want to travel like hundreds of kilometers, then you cannot travel on a battery pack that is like half charged, like up to 60-70%. It has to have 100% SOC in these cases. So imbalanced battery packs will not give you 100% SOC. So that is why this cell balancing is needed. So directly then again improves the range of the vehicle, and then also improves something called Coulombic efficiency. So Coulombic efficiency is how much of the chemical energy stored inside is being converted to electrical energy. So again, like as I said, if the cells were to continuously operate in these areas, its coulombic efficiency would drop rapidly. Yeah. So then these are all of the reasons which is why cell balancing is required. Yeah. So with this, we will take a now we'll now take a look at the different types of cell balancing methods. Okay. So we have self balancing, okay, which is a very basic form of balancing. There is no assistance needed here, right? Then there is passive balancing, which is one of the most common methods used in today's market, in today's battery management system market, right? And then active balancing, which is a bit more advanced. It requires electrical components like capacitors or transformers, through which like charge between two cells can be exchanged. And then finally, there is a type of balancing that has been very recently introduced. It's called lossless balancing. Yeah, where no electrical components are used. It's just managed purely through switches. So these are some of the commonly used methods. So we'll be discussing passive balancing with switched shunt resistors, active balancing with capacitor and transformer, lossless balancing, and we'll also discuss another type of balancing which has been like recently implemented. It's called dynamic balancing. Okay, so dynamic balancing. So with this, let's progress to the next part. Yeah. So self-balancing is a type of balancing that can only be done if the batteries are placed in a parallel circuit. Yeah. It's only possible when they're placed in a parallel circuit. So we know that in parallel arrangement, the voltage of all the cells put together is the same. Yeah. So whatever voltage V1 has, the cell number V1 here will be same as V2, will be same as V3. So all these cells put together will have the same output voltage V. Yeah. So because of this, if there is any few cells that are having like slightly different voltages, say for example, this is 1.1 volt and this is 1.3 volts, and this is 1 volt, and then this is 1.2 volts. So they'll be like small. If there are small differences, then over time, over an extended period of time, some small amount of energy will be like shifted between these few cells. Yeah. So like there'll be like 0.1 volts going here, and then there'll be like 0.1 volts coming from here. So from cell number V4 to V3, and also from V2 to V3. So all of these cells will eventually end up balancing each other, but this will happen after a very long time. Okay, it's a very slow process. It takes a long time, and this is again only possible in parallel arrangement. Yeah, which is why this isn't a method that is preferred in real life. And also this will only happen if the voltage differences are very small. Yeah. So well, why is it not possible in series? It's not possible in series because the voltages then would be added up and they will not be the same in the circuit. Yeah. So self balancing is a very basic way, but again it is not really used. I mean, right now in this current state, it is not being used. However, this was implemented many years ago, but then again it proved to be very slow. Yeah. So this is with respect to self-balancing. So now we look at passive balancing. So in passive balancing, these cells, you see here, these cells are connected in series with a resistor. Okay, they are connected in series with a resistor, which is called shunt resistor. Okay, these are called shunt resistor. Okay, so these shunt resistors are resistors that have very small amount of resistance. Okay, and there is a switch. Okay, here you can see these are switches, which you can see here, Q1, Q2, so on, Q4 up till Qn. These are switches, are also called MOSFETs. Are also called MOSFETs. Okay, so MOSFET is basically like a semiconductor switch. So here what happens is each cell is connected to a shunt resistor. Okay, and then it is connected, the whole circuit is then connected to a switch. Okay, So whenever there is an imbalance, either during charging or discharging, the control unit will sense that imbalance between these two cells. Suppose say cell number 1, V1, will have higher voltage, say for example 3.7 volts, and then V2 will have something like 3.3 volts. Okay, so the controller will sense this difference in voltage, and then what it will do, it will open the MOSFET of cell number 1. Okay, it will open the MOSFET or switch of cell number 1. Current then flows through this resistor. It flows through the resistor and dissipates its energy in the form of heat. Okay, it dissipates its energy in form of heat, and gradually 3.7 will be reduced till 3.3 volts is reached. Okay, so that's voltage of cell number 2. So this will be how the passive balancing works, right? So basically what the controller does, it prefers the battery to reach the lower voltage. So always it gives priority to the lower voltage, 3.3 volts. Okay, so likewise for the entire battery pack, let's say there are 4 cells. Let's say V1 has 3.7, V2 has 3.3, and then V3 has 3.5, but then V4 has 3.1. Okay, so then again the controller will give priority to the cell that has the lowest voltage, that is going to be V4, and it will open the switches Q1, Q2 and Q3, and it will allow all the cells to drain through the resistors R1, R2 and R3 till they all reach 3.1 volts. Okay, so that is how passive balancing is done through switch. Okay, this is why it is called switched shunt resistor. Why? Because there is a switch and there is a shunt resistor through which the cell can drain its energy. Okay, so this is always how passive balancing works, and that is the major drawback, that a lot of energy is wasted, right? And the complete energy of the battery pack cannot be utilized in this case. So even though you charge it fully, what happens is, if there's a small amount of imbalance, you will effectively not be able to use 100% of the capacity. Yeah? So this kind of method is not very efficient, but the advantage is that it is very simple to build, very simple to build, very simple to control, simple to implement in a circuit as well, and the control method is pretty simple as well. So controlling these switches and the programming and all the arrangements is not that complicated, right? So not much complication is needed here. But then, as I said, the disadvantage is that a lot of heat is generated, right? So that can cause a degrading of the circuitry. So that can even cause heating of the batteries also. So some of the heat that it is passing through the resistor can then start to heat up the cell also. Yeah. So these are so this is passive cell balancing. And usually if you want to implement a low cost, simple in terms of control as well, and in terms of building the circuit, and there are also ways to overcome this by implementing more efficient resistors and circuits. But yeah, still nevertheless it's not very efficient in terms of balancing. So that was for discharging. And for similarly for charging, let's say that these cells are being charged. So V1, V2, V3, V4 is being charged, and let's say that the charge voltage for V1 has reached 3.7 volts, for V2 it is 3.5, for V3 it is 3.4, and V4 it is 3.6. Okay, so here the controller will give priority to the voltage which is higher. Okay, so 3.7 volts is the higher one. Okay, so what it will do, the controller will stop charging V1. Okay, it will stop charging V1. Meanwhile, it will continue to charge V2, V3 and V4. And instead of charging V1, what it will do, it will start to dissipate its heat. It start to dissipate the energy through R1. It will open the switch. It will close the switch, or it will connect the switch, and it will force V1 voltage number cell number 1 to then start to discharge or start to drain its energy through R1. So while this is at 3.7, every other cell will be charged all the way till 3.7, and then it will stop charging. Okay, so this is how passive balancing is done during charging. Yeah. So this is passive balancing with switch shunt resistor. So you can see that an animation over here, how exactly the charging is limited because of like one of the cells which has reached the upper limit, right? So yeah, this will be your limit no matter what your cell is, no matter what your capacity of the battery pack is. So this will be your upper limit. So no matter how many cells you have, right? If they're in very good condition also, so they have n number of cells, all of their voltage will be like limited to this. Yeah, and as you can see, this portion is unlimited, unutilized or unused. So this will be wasted capacity. Yeah. So yeah. So this is during charging, and similarly, you'll also see the same effect during discharging as well. Yeah. So now we'll go into active balancing. So active balancing. So first one will be through a capacitor, through a single capacitor. Okay, there are two ways. One is through a single capacitor, the other one is through multiple capacitors. So we'll take a look at single capacitor. So like the arrangement is like pretty similar to the one with resistor, except that the whole battery pack, so whatever cells we have, will be shared with one single capacitor, and then each cell will have switches, like will have switches like which are basically MOSFETs. Okay, so these switches will activate based on whichever cell has whichever cells are having a difference in terms of voltage. Yeah. So for example, let's consider cell 1 and cell number 3. Okay, so let's say that cell number 1 has something like 3.5 volts and cell V3 has 3.9 volts. Okay, so what will happen? Q3 will close. So this is open right now. Q3 will close. Okay, the controller will sense this difference. Q3 will close, and what will V3 do? V3 will then discharge through Q3, go through the capacitor. Okay, and when the capacitor is filled, Q3 will then disconnect, which means Q3 will then open, capacitor will then discharge, and then it will go to V1. Okay, so at that point in time, even switch Q1 will close. Yeah, so this is how through a capacitor active cell balancing can be performed. But here the thing is that only two cells can exchange energy and not more than two cells. So what that means is it can either be from V1 to like V3 or V3 to V1, depending upon whichever cell is having, like whichever two cells are having bigger difference in voltage. So that means that even if there are multiple unbalanced cells, or if there are multiple cells with lower voltage, then balancing cannot be performed till V1 and V3 are balanced. So that is the most that is the feature of the active balancing method through single capacitor, right? Here losses are very low. Okay, so losses are much lower than resistive based method through passive based method. But here, as I said, only two cells can exchange energy at a time. Okay, so if other cells have to exchange, then it will take a lot of time, which is why like it's one of it takes a lot of time. There are a lot of delays in energy transfer, and sometimes even the capacitor will not have like immediate responses, right? It takes a long time to respond. Yeah, so with this way active balancing is performed. But the thing is that the controller has to be programmed. Okay, and here it requires like some complex programming, and like even the control algorithm is like much more complicated, right? So which is why it's more expensive to implement this, but in terms of efficiency it's like much higher than much higher than resistive based method. Okay, so this is active balancing with respect to single shared capacitor. So there'll be one capacitor. Yeah, so here we'll see multiple capacitors. So so there are like there are two pairs. I mean to say there is a pair of cells. So say B1 and B2, they will share one capacitor. So similarly, B2 and B3 will share a capacitor, and they will also be a capacitor common to all three of them put together. Yeah, so like this can go on. This can be like for n number of cells as well. So you'll have n number of pairs. So you'll have n number of individual capacitors and one shared capacitor for all of them. Yeah. So here, like it's not not limited like how we have for single capacitor. So like here, like what can happen is two cells can exchange at the same time, or even multiple cells can exchange through at the same time. Yeah. So for example, if I want to balance all three B1, B2, and B3, it can be accomplished through all of the three capacitors put together. Okay. So that way, like active balancing through multiple capacitors can be done, right? But again, here it is a very complex control algorithm, because like the switches, the states of the switches, and also the function and behavior of the capacitors, all three of the capacitors have to be monitored, right? So it's a much more complicated way of implementing this particular method. Yeah. So this is a brief look at the multiple switched capacitor, right? So the thing is that one major advantage is that it is much faster than the single capacitor method. So there is not much like waiting time here in case like multiple cells have to be balanced. So in case B1 and B2 are undergoing balance and B3 also has to undergo balance, then immediately the MOSFET will open up for C3 and balancing can be accomplished through here. Yeah. So yeah, this is with respect to multiple switched capacitor. And now we also have it through transformer. So similar to what we had in capacitor, there is also a transformer. So it's very similar to it, except that here induction coils will be used instead of a capacitor. Okay. So again, each cell will have a switch. So here you can see the switches. These are all MOSFETs again. Okay, n number of switches for n number of cells. There'll be a controller and there'll be one switch for the transformer. Okay. So whenever, let's say there's a difference between two cells, say B1 and B2, again, the controller will close the switches for B1 and B2 respectively, and the charge will flow through the transformer. So there's a primary induction coil and then there's a secondary induction coil. Okay. Primary, secondary. Okay. So primary and secondary induction coils. So as soon as B1 starts to discharge, so let's say that B1 is greater than B2 in terms of voltage. So what the controller will do, it will close switches S3 and switches S4. Okay. The cell B1 will start to discharge through S3. It will go to the transformer, charge up the primary induction coil, and then charge the secondary induction coil. And then it will flow into S2 and start to charge up battery number, to say cell number B2. Okay. So likewise, it can do it for like any other two cells. So for example, B1 and B3, or like B2 and B5. But again, this has the similar drawback to single capacitor based method. Yeah. And usually this kind of method is a bit slower compared to like capacitor based method, because it takes some time for the coils of the transformer to like charge up. So it won't be instantaneous. So this is with respect to transformer based, single transformer based, right? So yeah, then this works on the mutual induction principle. So like, yeah, transformer here, like mutual induction will happen, and that's how charge will be like sent from a primary coil to secondary coil, and then from there to cell number 2. Yeah. So this is with respect to one transformer. And then just like that, we can also use multiple transformers in the entire circuit. Okay. So here again, as I said, the exchange can happen between like any number of cells at the same time. So for example, if you want to balance B1 and B2, and at the same time you also want to balance like B3, so like all three transformers will work and the switches for each one will activate. Yeah. So, but for this, then a sophisticated control algorithm is needed, just like how we had seen in multiple switch capacitor. Yeah. So this way, like even a multiple transformer based method can be done. But again, here the delay will be have to be considered, because it's a bit slower than the capacitor method. Yeah. So this is with respect to passive and active. And now there is another method, something called lossless balancing. So here it doesn't use any electrical elements, right? Like no capacitor, no resistor, no transformer, nothing like that. It just uses only a MOSFET, or to say switches, and then the controller will handle all of the charging or discharging process. So basically what will happen, the controller will sense which cell have in terms of charging, which cell has reached maximum voltage, and then what it will do, it will disconnect the switch of that particular cell. Suppose this is the cell over here, cell number 4. Let's say it has reached maximum voltage. Okay, so what it will do, it will disconnect this. So this particular red line here means it is disconnected. Okay, so it is disconnected here. So what that means is cell number 4 has been isolated from the entire charging circuit, while 1, 2, 3, and all of the other ones will continue to charge. Yeah. So this way, it will continue charging till the voltage value of cell number 4 has been reached. Then, if further charging is required, then again the switch for cell number 4 will be open. It will be initially it will be open and then it will be closed. So then all of the cells will continue charging. Yeah. So this way, so in terms of charging and discharging, lossless balancing can be done. Yeah. So this way, even efficiently, the battery pack can utilize the energy of each cell, as well as prevent any losses due to heat or due to the transformer coils or due to capacitance. Yeah. So this way, lossless balancing will be achieved. Yeah. And this is much easier to implement compared to other types of circuits that we had seen before. So this doesn't require much complex algorithms or much complex programming. So all the controller has a very simple function, and that is with respect to the switch. So that switch will be for all the cells. Yeah. So this is with respect to lossless balancing. Okay. And now we look at one more advanced technique. It's called dynamic balancing. So what happens is the controller will be much more sophisticated in this case, and it will analyze or it will continuously sense the current being measured at each cell, the current being sensed, current being sent to each cell. Okay. So here, let's say we have a cell with limited capacity on the left hand side. So that's the weak cell. And then there is a strong cell which has a much higher capacity, right? So the thing is that the weaker cell will charge faster than the stronger cell. What that means, it will reach the higher voltage level much faster than the strong cell, right? If they were to be charged at the same rate. So what the controller will do, it will calculate how much current has to be sent to each cell, and accordingly it will adjust the charging current. So you can see on the left hand side, so it will send 0.7 amps, while the right hand side one, it will send 1 amp, right? So likewise, it can adjust for different types of cells. So this way, dynamic balancing can be adjusted. This way, the dynamic balancing can be achieved. So same way, you will be able to see it for discharging as well. Yeah. So here, some pretty sophisticated program is needed. Here, the battery management system has to use a bit more complex method of achieving this. At all points in time, the cell state of health must be known. So what that means is it must know the condition of the cell. How good is it? Is it still at its maximum capacity, or is it has it started to degrade? Then it must know the current and voltage values from each cell, and that way, with these information, it will be able to adjust for dynamic balancing. Yeah. So this is another way in which balancing can be done without using resistors and capacitors. Yeah. So yeah, this is with respect to dynamic balancing. So we'll come to the last bit. So here there is, we'll discuss in brief what exactly is, what are the different balancing algorithms, right? So the most commonly used one is cell voltage based algorithm, balancing based on cell voltage. Okay. So the voltage that is being measured at the terminal voltage, the terminals of the cell. Okay. And then the second one is state of charge. Okay. It's a bit more advanced, a bit more sophisticated than cell voltage. And then the third one is neural network based, something called outlier based detection. Okay, where a very advanced neural tracking algorithm is used. Where it will utilize some pretty advanced programming approach in order to balance the cells. Yeah. So we'll take a brief look. at all of them. So voltage based balancing is pretty simple. So each cell will have a voltage sensor, and it will measure the open circuit voltage and terminal voltage of each cell with of each cell of the battery pack. Yeah. So if there is differences noted between two cells or two or more cells, and if that difference is larger than a particular threshold value, so there'll be a particular threshold value for the difference in the voltage, and if the difference is higher, then the controller will start the balancing procedure. So it will start to balance all of the cells. Yeah. But like the major drawback is only voltage can be controlled in this and not more than that. So like there won't be much importance given to current as such, and only the priority will be given to voltage. Yeah. And like as I said, like this will be like the passive balancing will be limited to voltage based voltage based balancing. Yeah. So this is a pretty simple way. It's the simplest method. It's very cheap to implement, but then you have to account for voltage variations. Yeah. So this is balancing with voltage, so cell voltage. So this is the simplest method, but sometimes it cannot be like used accurately. So that's where like SOC based balancing algorithm is used. Yeah. Where the lithium ion the battery parameters, that is the state of charge, the current and voltage, all three of them, right? So if you know all three of them, if the controller and the battery management unit is able to sense, calculate and measure all these three parameters at the same time, then basically it is able to have a much more accurate control of the cells balancing process. And also like at the same time, even the capacity of the cells at the same time is known. Yeah. So right, but one of the major problems is that if you have to estimate SOC, you will need current sensors. Okay. And from current sensors, usually like the entire battery pack will be having limited number of current sensors. So like having a current sensor for each and every cell is not it's not feasible, it's not practical. So in that way, determining the state of charge for each and every cell is a little bit challenging, right? And yeah, it won't give you an exact control over the voltage and current of the cell. Yeah. But usually it gives you much more accurate control over the balancing process. Yeah. So the last one is outlier based detection. So this, as I said, it is a tracking algorithm. The tracking algorithm. So this tracking algorithm is based on neural networks, okay, where there are certain values and parameters that will be calculated, okay, and if certain conditions are met, like for example, there are attributes. As I said, attributes are parameters like voltage, state of charge, energy, capacity. All these are all these values will be estimated using certain algorithms, and if they are all equal, then that means that the entire battery pack is balanced and the balancing procedure will not take place. Yeah. But if it is not satisfied, right, if the results that are seen are not equal, right, then there are certain standardized processes that will take place, and it will guess the outlier cell. So outlier cell is which group of cells are having voltage difference greater than the mentioned threshold value. Okay. And if these threshold values are measured correctly, then it will go ahead and start the balancing of the cells. Yeah. So with this, like it's a very complex process. Like I mean, I will not be able to explain the whole process here, but it's based on a series of algorithms, iterative process, which will continuously check over and over which cells are outside the nominal value or threshold value, and based on that, the balancing will be completed. Yeah. So this is with respect to outlier detection method. Um, and yeah, in these ways, like cells can be balanced, right? So yeah, with this we conclude today's webinar. Thank you all for attending today's session. So now we can have a look at some of the question answers. So if anyone has any question answers, we can now look into that. So yeah, there are some questions here. Yeah, so even if we configure the lower voltage cutoff, then also sometimes cell goes into deep discharge. No, I think this question is from Mahadev. Like, no, you see, the thing is that the battery management system will continuously sense the voltage, lower and upper. It will know the limits. So the microprocessor inside it will know, and it will be able to like sense immediately which cell is having the lower voltage, whichever cell is going to the lower voltage, and it will immediately cut off that particular cell from the circuit. Okay. So it will not enter deep discharge if the battery management system is configured correctly.